In this video, we are going to discuss quadratic functions and models. In our discussion about quadratic functions, we have three learning objectives. Some of them are pieces that you would have covered in previous classes, and so part of this should be a little bit of a review from your earlier work. But we are going to analyze the graphs of quadratic functions. We will write quadratic functions in standard form, and then use the standard form to sketch the graph of a quadratic function. And we will also find the minimum and maximum values of quadratic functions in applied problems, that is the real-life application. You can see at the bottom of the screen that we have several pieces of vocabulary, and we will define some of them in the video with writing, but not all of them will be written down. Some of them will be presented only verbally. Starting off, a piece that should look very familiar. What's a polynomial? Well, it's a type of function that has this particular format where you have real numbers that is multiplied by a power of x. So x to the n, keeping in mind that the first number, a sub n, which is called the leading coefficient, your leading coefficient cannot be 0. And we also require that every single exponent is a non-negative integer. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Keep counting, you're good to go. But if you're trying to use negatives or fractions or decimals, that's not going to work. When you write out your polynomial, the largest exponent on your x's is called the degree. Now, although we can look at polynomials, our work today is not about the general polynomial. It's about one specific type, quadratics. Quadratics are polynomials that are a degree of 2, so the largest exponent on your x's is a 2. And therefore, it has to have the form a2 x times x squared plus a1 times x plus a0. Most of the time, people do not present quadratics using a2, a1, and a0. They generally just use a, b, and c. And we will follow this convention throughout the rest of the video. A squared plus b squared plus c is the format for quadratics. Now, this is frequently referred to as general form. It's not the same thing as standard form. And even these pieces about general versus standard, different authors actually argue about what should be general form, what should be standard form. And so depending on your textbook, they might actually give you different names for the same thing. They might get conflicted because authors actually argue in their writing about what should be called what. You're probably familiar with the U shape of quadratic functions. They have this general shape. You should also remember that this general shape is called a parabola. The function, that is the algebraic equation, is called a quadratic, but the picture, your graph, is a parabola. There are some important pieces of information that sometimes students forget about parabolas. So let's take a minute and review some of the important characteristics, some of the important vocabulary to make sure that we understand when we're communicating with each other. Here's a list of vocab. Where is the vertex? Well, you'll remember, if we have our general U shape, the vertex is this point down at the bottom. The axis of symmetry. Every single parabola can be folded in half and have them match up. The place that you fold across is called the axis of symmetry. For this particular one, and I intentionally put it a little bit off the y-axis, But if we were to fold the left and the right-hand side across this red line, they should match up. You'll note the axis of symmetry is actually going through the vertex. That is guaranteed to happen every single time. A nice way of phrasing it is like the axis of symmetry is in the middle of the graph if you folded it across the middle. Okay, our third piece that we're looking at is opens upward. Think of the parabola almost like a bowl. If this were shaped, if we had this little bowl sitting here, would you say the bowl is pointing up or pointing down? This is one that you would say a bowl is up. So this is one that we would describe as opens upward. There is a nice condition if you're talking about parabolas that open upward. Opening up is determined completely and totally by the leading coefficient. If you have a leading coefficient that is greater than 0, so if it's positive, your parabola will always open upward. If you take the opposite approach, though, and have a negative, whoa, that's not the color I wanted. Let's go with this. If you have a negative leading coefficient, that will have an opposite effect so that your parabola is going to be like an upside down bowl, which we would describe as opening downward. Depending on whether or not your parabola opens up or opens down, you would notice that the vertex has some interesting characteristics to it. In the blue parabola that opens upward, this vertex is actually lower than every single other point on the graph. Every other point in blue is higher than the vertex. In this instance, we would talk about the minimum. Minimum, of course, meaning smallest. But here's where a lot of students get some confusion. The point itself is not the minimum. The point is the vertex. Minimum refers only to the height of the point. That is the y-coordinate. The minimum is not talking about the location, it's talking about how far down on the y-axis are you. The lowest point, the lowest height on the y-axis is the minimum. Likewise, when we're looking at the maximum is not the vertex. The maximum is occurring at the same height as the vertex. If we were to come over from the vertex and hit the y-axis, it's this height in purple that's the maximum. Maximum and minimum refer to the height up or down, not a point on the parabola. You'll notice the question posted at the bottom. How can you use the equation for a quadratic function to predict the basic behavior? Well, the basic behavior is tying into what we were just mentioning. A leading coefficient that's positive is going to open up. A leading coefficient that's negative will open down. We can use the leading coefficient to get general behavior, but we would also need to know the location of the vertex. That is a piece that we are going to discuss in an upcoming part of the video. Here's our first example that we will look at. We have two graphs, y equals x squared and y equals 2x squared. Compare them. Well, we'll start by creating the pictures. That way we have something to look at. So I'm going to do y equals x squared, the parent function, in blue. And 2 squared would give me 4. Negative 2 squared is also 4. And so we would have a function that is similar to this. Or here's a sketch of y equals x squared. And I'm going to switch to red to do our f of x equals 2x squared. Graph it any way you want. You can use transformations. You can use an input-output table. You can plot points. Use whatever technique you'd like. But you should be able to obtain this set of points. And there goes up to 8. Okay, so here are the two graphs of y equals x squared and f of x equals 2x squared. Directions didn't say graph, they said compare. So how are they alike? How are they different? Let's compare and contrast them. What are some characteristics that these two parabolas have in common? How about the obvious one? They're both parabolas. That's kind of the easy one. And we could elaborate further that open up. They open upward. And what about the vertex? And they have the same vertex. And it happens to be the origin. So there you go. 3 quick things that they have in common. They're parabolas, they both open up, they both have the same vertex at the origin. There's a compare. The directions do not specifically state contrast, but we should anyway. If you're going to talk about how things are the same, it's beneficial to talk about how they're different as well. So what's different about these parabolas? Okay, one's smaller, one's bigger. There are many different correct ways to phrase it. For this particular one, I would phrase it as f of x equals 2x, rises faster than y equals x squared. And there are lots of other ways that you could phrase it. This is just the way that pops into my brain and the words that came to my mind. And I think of them as rising faster because both of them started off down at the origin. But the blue, by the time we get over to an x of 1, has only got up to 1. But the red has already reached a height of 2. It's getting up higher, faster. And when we get over to 2, the blue is at a height of 4, but the red is up to a height of 8. It's getting up higher, faster. It's just the way my brain saw it, the way my brain described it. One of several different correct answers. Similar problem. Y equals x squared. G of x equals half x squared. Well, let's start by redoing our parabola that we had. Here's our y equals x squared that we had before. Again, just doing a quick sketch. Oh man, that quick sketch kind of messed me up. And then half x squared would be half 2, and then 8 would be down at 4. And so we'd have this general shape. So let's compare them. What's the same about them? Well, I'm going to cheat here. I'm going to cheat and go back to what I had before and just copy all the piece that I had on the last one. And I'm bringing it forward because I'm going to be a little bit lazy and save myself some time. But once again, they're both parabolas. They both open upward. They both have the same vertex of 0, 0. So it's kind of nice to simply say all the stuff in green is still the same. But in the yellow, not so much anymore. F of x equals 2x squared rose faster, but we don't have 2x squared. Now we need to change this so that instead of having f and 2, I'll switch it to purple. We have g of x, which is 1/2 x squared. Is it still rising faster than y equals x squared? Not on this one. This is one where instead of being at a height of 1, it's at a height of 2. Instead of being at 4, it's half as tall for a height of 2. So this is one that's actually rising slower. And my E does not look much like an E. But there we go. We can compare, we can contrast, we can talk about how they're the same and how they're the different, just identifying the behavior of our parabolas. And if you wanted to use some analysis on the equations of the quadratics, we'd be able to discuss even more. All right, standard form for quadratic. We'd mentioned before that general form is ax squared plus bx plus c. Standard form is a different way of writing it. Specifically, it has this form where we're still using the same leading coefficient. A is still the exact same A that we were talking about before. It's the coefficient in front of the x squared term. And like before, it still cannot be 0, otherwise we don't even have a quadratic at all. But where it's different is that h and k are actually going to be the coordinates of the vertex. Where this gets to be so beneficial is if we are able to take a quadratic that was written in the general format and rewrite it so that it is in standard form. It is much, much easier to graph in standard form than general form. Way easier. Because when we know the vertex, it tells us where the axis of symmetry is. So we can do the left and the right, or depending on the type of parabola, an up or down. But we can get all the points much quicker, much easier if we're using standard form. Now for our example 3, we have a couple different pieces. First, sketch the graph of f of x. Then we want to identify the vertex and the axis of symmetry. Now if we wanted to, we could create an XY input-output table, plot a bunch of points, and get the graph. Completely valid technique. I don't want to do it that way. I would much rather take advantage of standard form. If we can use some algebra to rewrite this equation into a different format, specifically into standard form, then we can get the vertex instantly, we can get the axis of symmetry instantly, and we could quite quickly get some of the other points that will allow us to graph the function. And I noticed I got the x, so I got to erase this and fix it. A student actually pointed it out, so that's a good thing. Paying attention, making sure I don't mess it up. Good job. Okay, so you notice with standard form, it's a plain x inside. We're going to do the same thing. We are going to factor out a 3 from this piece with the x's. Well, if we factor out the 3, what's left? X squared minus 8x. This is relevant for us because with the 3 gone, we are able to say what is the missing piece that will allow us to complete the square. If you don't remember how to complete the square, you may want to leave this video, find another one, and just do some research on YouTube, completing the square. Component that we need to do, take the middle term, cut it in half. That's -4. Take -4 and square it. That gives us plus 16. Well, because we added 16, we can't just randomly start adding 16 wherever we want. So we are going to have to subtract off 16 at the same time. That part is beneficial for us because you'll notice plus 16 and minus 16 is 0. All we've done is add 0. But this is really beneficial because it allows us to take these three terms and rewrite them in the format of x minus 4 quantity squared. Then we'll have the little leftover yellow piece of minus 16. You'll note we are now closer to having standard form. You see how we have the x minus 4 quantity squared? That's our x minus h. To continue the problem, I'm just going to distribute the 3 across. So we'd have 3x minus 4 quantity squared. 3 times 16 is equal to 48. And we still have this 49 on the outside, so that would tell us 3x minus 4 quantity squared plus 1. And voila, this is standard form. The reason we care so much about this is to create a quick sketch. We know 4 is the x-coordinate for the vertex. We know positive 1 is the y-coordinate for the vertex. Just looking at it, we already have this point. Secondly, because this is a positive 3, because it is positive, we know it's going to open up. Because it is 3, we know that if we're going to go left or right 1, we'll have to go up 3. Right 1, 1, 2, 3. That's where a point's going to go. Left 1, 1, 2, 3. And so we're able to get those points based on it being a positive 3, which could just let us connect the dots, and we have a quick sketch of what the function would need to look like. Okay, backing up, the question was asked, how did I get the other points? In a normal parabola centered at the origin, so the parent function, you would have the point 1, 1, so you'd go right 1, up 1. And you can also go left 1, up 1 to get those 3 points on the normal just x squared. But this is a 3. So we will still do the same left 1 and right 1 from the vertex. But instead of going up 1, we can go up 3. Because the leading coefficient was 3. So it's saying right 1, up 2, up 3. Here's where a point would go. And if we did the left-hand side, left 1, up 2, up 3, giving us the other point. We're just taking advantage of the leading coefficient being 3 to fill in the details and get our general sketch. We were still asked to name the vertex. We already did that. It's at the bottom, 4, 1. We were asked to name the axis of symmetry. I left off the y in symmetry. This is also really straightforward. Our axis of symmetry is right down the middle. It's a vertical line passing through the vertex. Vertical lines have the form x equals, and x-coordinate on the vertex was 4, so we're instantly done. Getting standard form allows us to get the vertex and axis of symmetry very, very quickly. Getting the leading coefficient allows us to create the quick sketch of how far up and how quickly it needs to rise very, very quickly. Yes, we have to do completing the square algebra to get the answer, but it's not so bad when you consider the alternative was picking like 5 or 6 or 7 points and then just randomly hoping that we picked good points. Similar type. Sketch the graph. Do you notice how it's negative x squared? Negative x squared is telling us that this is going to open downward. So one way that we can do this, and there are several different correct ways to write it up, is to factor out the negative, which would give us x squared plus 4x plus 3. We would still need to do completing the square. So I'm going to look at it and say x squared plus 4x. What is the piece I'm going to need for completing the square? Well, take the 4 and cut it in half. That's 2. Take the 2 and square it. That's 4. In order to complete the square, I need this number to be a 4. But I actually don't have 4. I only have 3. So what am I going to have to do? If I need 4 and I have 3, what can I have written here that's still going to be 3? If I took 4 plus 1, 4 plus 1 is 5. That's not the 3 that we actually have. Instead of 4 plus 1, I could write it up as 4 minus 1. In which case, 4 minus 1 actually does match the 3 that we wanted. It does give us the piece we need. And so we could use completing the square now. Still have the minus, but then these 3 pieces I'm underlining in yellow, those could be rewritten as x plus 2 quantity squared. And we just have our minus 1 on the outside. Distributing the negative across, we'd have negative x plus 2 quantity squared. And the minus negative 1 would be plus 1. And there we go. We have our standard form. In this instance, we could see the leading coefficient is actually negative 1. It's a case of the unwritten 1. We could see the vertex, just changing the sign, negative 2, keeping the sign for the y value, positive 1. So we could graph it now. Negative 2, 1 is the vertex. Because the leading coefficient is negative, we know that it's going to open downward. And because it's 1, it tells us if we go a little bit, plus or minus left and right 1, the height is going to go down 1. So right 1 down 1, left 1 down 1. We get our 3 points for the general quadratic. And we could have a quick sketch, understanding it's not perfect, but it's a quick sketch with our 3 points, getting the main behavior of the curve of the u, getting the curve of our parabola. So, where is the vertex? We have that answered in the yellow. The next part, though, does not ask for the axis of symmetry. It asks for the x-intercepts. Remember, the x-intercepts have the characteristic right here that the height is 0. Well, we're pretty fortunate. We can see exactly where it's crossing the x-axis. What are the x values where it's crossing? From right there, we can see it's crossing at x equals negative 3 and x equals negative 1. We can get the x-intercepts directly from the graph. And we're lucky that we don't need to do some extra algebra to figure it out. In this instance, creating the graph allowed us to get those values very, very quickly. If it didn't work out to be so nice, and we needed to do algebra to get the x-intercepts, one could make the argument that the quickest way of doing that is to go back up to the original and solve the equation, when is it equal to 0? If you solve that equation, you should be able to get the values for the x-intercepts. Last one that we have. Write the standard form of the parabola whose vertex is 1, 2, and it passes through the point 3, negative 6. Well, that's telling us we have a piece that's like, okay, the vertex is 1, 2, 2, 3, 1, 2, 3, 4, 5, 6, and 3, negative 6. So we would have this piece that's coming down, 2 to the right, 1, 2, 2 to the left. I'm taking advantage of the axis of symmetry to create the graph. What is the equation in standard form for that? Keeping in mind that my ability to draw is not that beautiful. Well, we're lucky because we have standard form. Standard form will tell us we need the leading coefficient, x minus h quantity squared plus k. And so we can get that. We can plug in h and k. We have a, the x value for the vertex is 1, and the k value is 2. Here is our function in standard form. But we do have this problem. We don't know what the a value is. We will need to use the other point. We can use the point 3, negative 6 to figure out what the number a actually is. In order to do that, we are going to plug in the x value of 3, which we know will give us the y value of negative 6. So that tells us our y value is negative 6. The x value, we plugged in 3. And now we just need to solve this equation. If we can get that equation, then we will be finished with our work on standard form. 3 minus 1, that's 2. 2 squared gives us 4. So a times 4 plus 2. Subtract off the negative, subtract off the 2. Negative 8 equals a times 4. Dividing by 4 would tell us a is equal to negative 2. And it's really nice that we're seeing negative 2, because since it opens downward, we know it had to be a negative number. That's just a quick little extra piece of verification to help us feel better about our work. But we can take that negative 2, plug it right back in, and we have our equation. In standard form, we're finished. The last piece that we need to know about quadratics was specifically, we were talking about the maximum and the minimum values. We know the maximum and minimum, either the height, the highest point or the lowest point, is going to occur at the vertex. So we have particular interest in figuring out, if we have a maximum, where is the vertex? And if we have a minimum, where is the vertex? Fortunately, we have a formula that will give it to us. If you have a quadratic in the general form, ax squared plus bx plus c, the vertex is located when you have x equals negative b over 2a. I strongly recommend you memorize that because it is massively helpful. It is a huge time saver when you're doing word problems. Word problems that deal with quadratics are almost always about where is the vertex, what is the maximum, what is the minimum. And this is a strategy that is guaranteed to get you that every single time. It always works. So, putting it together, we know, going back from the beginning, that if the leading coefficient is positive, that tells us it's going to open upward. If it opens upward, do we have a maximum? Look at the graph. A is greater than 0 does not lead to the picture of having a maximum. We can't just blindly start putting pieces in. But if we do A is less than 0, then we know it opens downward, and that is something that has a maximum. The maximum occurs when x is equal to negative b over 2a. But the x value is not the maximum. The point is not the maximum. The maximum is actually the y value. After you figure out what the x is, you will have to plug it back into the function. When you plug it back into the function and crunch your numbers, it will give you the maximum. Or in the instance when you have a positive leading coefficient, the exact same technique of using negative b over 2a to get the x, and then using x to plug into the function and getting the y, that will give you the minimum. And here actually is the last thing we're going to look at. Example 6. A baseball is hit at a point 3 feet above ground at a velocity of 100 feet per second and at an angle of 45 degrees with respect to the ground. All of that is basically just saying, hey, somebody hit a ball. The path of the baseball is given by this particular function. I will point out, though, in a higher level math class, they will not give you the function. They will just say, it's hit 3 feet above the ground, it's given the speed, it's given the angle, and using math, you can actually create this function for you. We do not yet have the tools to create that function, which is why we're giving it to you. But it actually does work out. If you really did have this situation hit, it really will follow this function perfectly. But f of x is the height of the baseball above ground. X is the distance along the field horizontally from the home plate. What is the maximum height reached by the baseball? Well, here's the big thing worth noting. F of x is equal to negative 0.0032 x squared plus x plus 3. This is a quadratic. Quadratics reach their maximum at x equals negative b over 2a. So with negative b over 2a, what's the b value? B is 1, so we'd have negative 1 over 2 times the a value, negative 0.0032. Well, grab your calculators. Let's start crunching some numbers. I'll pull this one up and say, oh, go here. We'd have menu, add the calculator, 1 divided by 2 times negative 0.0032, close parentheses. Oh, I had a positive 1. It was supposed to be a negative 1, which is going to change it from a negative 156 to a positive 156. But we get 156.25. This is the x value where it's going to reach its maximum height. That's saying when we have the guy standing here, there's his bat, and the ball is hit, this maximum peak is coming 156.25 feet away. But we want to know how high is that maximum peak. And we could do some trigonometry to figure that stuff out, because we know it was a 45-degree angle, we know it had a height of 3, but more generally, it's easier just to say, this is x. Plug in x into the function. If we did the substitution, we'd have our answers. So coming back, we have negative 0.0032 times 156.25 squared plus 156.25 plus 3. Just substituting x into our function. There we go. 81.125. The highest point that the ball will actually reach is 81.125 feet. So 81 1/8 feet off the ground. Yay, we're happy. I would like to ask for your class, do you use a lot of graphing calculators to help you out with problems? I have to admit, I do not have a TI-84 on my computer, at least not a digital version, and so I can't create the recording of it. But the technique is still going to be the same, where we could plug this piece into a graph, and then have you used the maximum feature of the graph yet? If you typed this function into the calculator, and then did the maximum feature of your graphing calculator, it will tell you what the point is. It will give you both the x value and the y value. You just have to know how to interpret the x and the y value to finish it off. So, finally shutting up for the day. For quadratic functions and models, we had the 3 learning objectives. You should be able to analyze the graphs. Analyzing the graphs is about doing opens upward, opens downward, where's the vertex, where's the axis of symmetry, all of those pieces. You should be able to use completing the square to write a quadratic function in standard form. You should use standard form to sketch a quick graph. And you should be able to use that formula to get the maximum and minimum values so that you can solve real-life problems like this baseball one and a number of other problems that get used.